Bill Gates' book, How to Avoid a Climate Disaster. Chapter 1. Why zero? The reason we need to get to zero is simple. Greenhouse gases trap heat, causing the average surface temperature of the Earth to go up. The more gases there are, the more the temperature rises. And once greenhouse gases are in the atmosphere, they stay there for a very long time. Something like 1/50 of the carbon dioxide emitted today will still be there in 10,000 years. There is no scenario in which we keep adding carbon to the atmosphere and the world stops getting hotter. And the hotter it gets, the harder it will be for humans to survive, much less thrive. We don't know exactly how much harm will be caused by a given rise in the temperature, but we have every reason to worry. And because greenhouse gases remain in the atmosphere for so long, the planet will stay warm for a long time, even after we get to zero. Admittedly, I'm using zero imprecisely, and I should be clear about what I mean. In pre-industrial times, before the mid-18th century or so, the Earth's carbon cycle was probably roughly in balance. That is, plants and other things absorbed about as much carbon dioxide as was emitted. But then we started burning fossil fuels. These fuels are made of carbon that's stored underground, thanks to plants that died eons ago and got compressed over millions of years into oil, coal, or natural gas. When we dig up those fuels and burn them, we emit extra carbon and add to the total amount in the atmosphere. There are no realistic paths to zero that involve abandoning these fuels completely or stopping all the other activities that also produce greenhouse gases, like making cement, using fertilizer, or letting methane leak out of natural gas power plants. Instead, in all likelihood, in a zero-carbon future, we will still be producing some emissions, but we will have ways to remove the carbon that they emit. In other words, getting to zero doesn't actually mean zero. It means near net zero. It's not a pass-fail exam where everything is great if we get a 100% reduction and everything is a disaster if we get only a 99% reduction. But the bigger the reduction, the bigger the benefit. A 50% drop in emissions wouldn't stop the rise in temperature. It would only slow things down, somewhat postponing but not preventing a climate catastrophe. And suppose we reach a 99% reduction, which countries and sectors of the economy would get to use the remaining 1%. How would we even decide something like that? In fact, to avoid the worst climate scenarios, at some point we will not only need to stop adding more gases, but actually need to start removing some of the gases we have already emitted. You may see this step referred as net negative emissions. It just means that eventually we will need to take more greenhouse gases out of the atmosphere. Then we put in, so that we can limit the temperature increase. To return to the bathtub analogy from the introduction, we won't just shut off the flow of water into the tub, we will open up the drain and let water flow out too. I suspect that this chapter will not be the first place you have read about the risks of failing to get to zero. After all, climate change is in the news just about every day, as it should be. It's an urgent problem, and it deserves every headline it gets. But the coverage can be confusing and even contradictory. In this book, I'll try to cut through the noise. Over the years, I've had the chance to learn from some of the world's top climate and energy scientists. It's a never-ending conversation because researchers' understanding of the climate is always advancing as they incorporate new data and improve the computer models they use to forecast different scenarios. But I found it enormously helpful in sorting out what's likely from what's possible but not probable. And it has convinced me that the only way to avoid disastrous outcomes is to get to zero. In this chapter, I want to share some of what I've learned. A little is a lot. I was surprised when I learned that what sounded like a small increase in the global temperature, just 1 or 2 degrees Celsius, which is 1.8 to 3.6 degrees Fahrenheit, could actually cause a lot of trouble. But it's true. In climate terms, a change of just a few degrees is a big deal. During the last ice age, the average temperature was just 6 degrees Celsius lower than it is today. During the age of the dinosaurs, when the average temperature was perhaps 4 degrees Celsius higher than today, there were crocodiles living above the Arctic Circle. It is also important to remember that these average numbers can be obscure a pretty big range of temperatures. Even though the global mean has gone up just 1 degree Celsius since pre-industrial times, some places have already started experiencing temperature increase of more than 2 degrees Celsius. These regions are home of between 20% and 40% of the world's population. Why are some places heating up more than others? In the interior of some continents, the soil is drier, which means the land can't cool off as much as it did in the past. Basically, continents aren't sweating as much as they used to. So what does a warming planet have to do with greenhouse gas emissions? Let's start with the basics. Carbon dioxide is the most common greenhouse gas, but there are a handful of others, such as nitrous oxide and methane. You might have enjoyed nitrous oxide at the dentist's office. It's also known as laughing gas. And methane is the main ingredient in the natural gas that you might use to run your stove or water heater. Molecule for molecule, many of these other gases cause more warming than carbon dioxide does. In the case of methane, 120 times more warming the moment it reaches the atmosphere. But methane doesn't stay around as long as carbon dioxide. To keep things simple, most people combine all the different greenhouse gases into a single measure known as carbon dioxide equivalents. You might see the terms abbreviated as CO2e. We use carbon dioxide equivalents to account for the fact that some gases trap more heat than carbon dioxide but don't stay around as long. Unfortunately, carbon dioxide equivalents are an imperfect measure. Ultimately, what really matters isn't the amount of greenhouse gas emissions. What matters is the higher temperatures and the impact of on humans. And on that front, a gas like methane is much worse than carbon dioxide. It drives the temperature up immediately and by quite a bit. When you use carbon dioxide equivalents, you aren't fully accounting for this important short-term effect. Nevertheless, they are the best method we have for counting emissions, and they come up often in discussions about climate change. So I use them in this book. The 51 billion tons I keep mentioning is the world's annual emissions in carbon dioxide equivalents. You may see numbers like 37 billion elsewhere. That's just carbon dioxide without the other greenhouse gases. or 10 billion, which is just the carbon itself. For the sake of variety, and because reading greenhouse gas 100 times will make your eyes glaze over, I will sometimes use carbon as a synonym for carbon dioxide and the other gases. Greenhouse gas emissions have increased dramatically since the 1850s due to human activity, such as burning fossil fuels. Check out the charts on page 24. On the left, you can see how much our carbon dioxide emissions have grown since 1850, and on the right, you can see how much the average global temperatures has gone up, like 5 degrees Celsius as high, 2 as lower, and 1 as negative. Most climate change reports use the Celsius scale for reporting temperature changes. I will follow that practice in this book because that's what you see in most news and reports. To get an idea of a temperature change in Fahrenheit that is accurate enough for most purposes, you can just double the Celsius number and remember that your estimate is a little high. Since most Americans think more naturally in Fahrenheit, I will use the scale when I'm referring to daily temperatures. How do greenhouse gases cause warming? The short answer: they absorb heat and trap it in the atmosphere. They work the same way as greenhouse works, hence the name. You're actually seeing the greenhouse effect in action on a very different scale whenever your car is sitting outside in the sun. Your windshield lets sunlight in, then traps some of that energy. That's why the interior of your car can get so much hotter than the outside temperature. But that explanation only raises more questions. How can the sun's heat get past greenhouse gases on its way to the earth, but then dioxide works like some giant one-way mirror? For that matter, if carbon dioxide and methane trap heat, why doesn't oxygen? The answers lie in the neat bit of chemistry and physics. As you may recall from physics class, all molecules vibrate. The faster they vibrate, the hotter they are. When certain types of molecules are hit with radiation at certain wavelengths, they block the radiation, soak up its energy, and vibrate faster. But not all radiation is on the right wavelengths to cause this effect. Sunlight, for example, passes high through more greenhouse gases without getting absorbed. Most of it reaches the Earth and warms up the planet, just as it has been doing for eons. Here's the problem: the Earth doesn't hold on to all that energy forever. If it did, the planet would already be unbearably hot. Instead, it radiates some of the energy back towards space, and some of this energy is emitted in just the right range of wavelengths to get absorbed by greenhouse gases. Rather than going out harmlessly into the void, it hits the greenhouse molecules and makes them vibrate faster, heating up the atmosphere. By the way, we should be thankful for the greenhouse effect. Without it, the planet would be far too cold for us. The problem is that all these extra greenhouse gases are sending the effect into overdrive. Why don't all gases act this way? Because molecules with two copies of the same atom, for example, nitrogen or oxygen molecules, let radiation pass straight through them. Only molecules made up of the different atoms, the way carbon dioxide and methane are, have the right structure to absorb radiation and start heating up. So that's the first part of the answer to the question, why do we have to get to zero? Because every bit of carbon we put into the atmosphere adds to greenhouse effect. There is no getting around physics. The next part of the answer involves the impact that all those greenhouse gases are having on the climate and on us. What we do and what we don't know. Scientists still have a lot to learn about how and why the climate is changing. IPCC reports acknowledge upfront some uncertainty about how much and how quickly the temperature will go up. For example, and exactly what effect these higher temperatures will have. One problem is that computer models are far from perfect. The climate is mind-blowing complex, and there's a lot we don't understand about things like how clouds affect warming and on the impact of all this extra heat on ecosystems. Researchers are identifying these gaps and trying to fill them in. Not everyone will suffer equally from hotter and more humid weather. For example, the Seattle area where Paul and I moved Microsoft in 1979 will probably get off relatively easy. We might reach 90 degrees and on as much as 40 days a year later this century, after having an average of just one or two a year in the 70s. And some having an average of just one or two, and some places might actually benefit from a warmer climate. In cold regions, for example, fewer people will die of hypothermia and the flu, and they will spend less money to heat their homes and businesses. These stronger storms are creating a strange feast of famine situation. Even though it's raining more in some places, other places are experiencing more frequent and more severe droughts. Hotter air can hold more moisture, and as the air gets warmer, it gets thirstier, drinking up more water from the soil. By the end of the century, soils in the southwestern United States will have 10% to 20% less moisture, and the risk of drought there will go up by at least 20%. Droughts will also threaten the Colorado River, which supplies drinking water for nearly 40 million people and irrigation for more than 1/7 of all American crops. A hotter climate means that there will be more frequent and destructive wildfires. Warm air absorbs moisture then from plants and soil, leaving everything more prone to burning. There is a lot of variation around the world because most conditions change so much from place to place. But California is a dramatic example of what's going on. Wildfires now occur there 5 times more often than in the 70s, largely because the fire season is getting longer and the forests there now contains much more dry wood that's likely to burn. According to the US government, half of this increase is due to climate change, and by mid-century America could experience more than twice as much destruction from wildfires as it does today. This should be worrisome for anyone who remembers America's devastating wildfire season of 2020. Another effect of the extra heat is that sea levels will go up. This is partly because polar ice is melting and partly because seawater expands when it gets warmer. Metal does the same thing, which is why you can loosen a ring that's stuck on your finger by running it under hot water. Although the overall rise in the global average sea level, most likely a few feet by 2100, may not sound like much, the rising tide will affect some places much more than others. Beach areas are in trouble, not surprisingly, but so are cities situated on especially porous land.